Okay, hello everyone. This session is about limit points of a set. So we are dealing with sets in real space. So let me define a limit point of a set. A real number L is a limit point of a set S subset of R if every neighborhood of L contains an infinite number of members of S. Infinite number of members of S. So before we analyze this definition, let me define another definition of a limit point. Let me give you another definition of a limit point, and we shall analyze how one implies the other. So second definition, which is more common and which you all have learned in your masters, is a real number L is a limit point of a set S subset of R if every neighborhood of L contains at least one member of S other than L. So a vague picture of what a limit point can be. So everyone would have played a game which is called Lake and the Land, correct? So the inner part of this oval or an ellipse is lake. In your childhood days you would have played this, and the outer part is nothing but the land. The red part is the land. So if children or who are playing, if one person shouts lake and the land continuously, so the other players should either step inside the circle and outside the circle according to the call of this person. So what happens if that person steps on the border here, that is the black ellipse? If the person steps on the border, the person is considered to be out or out of the game, correct? Why? Because whichever small part of your feet you try to place it on the line, you are sure that some part of the foot will touch the lake or it will touch the land. So if a person is asked to get inside the lake, the whole of the foot should be inside the ellipse, not on the border, because some part will surely be on the land. So that's why this black line is called as an limit or a boundary, correct? So this is a vague explanation. So analyzing our definition 2, we understand that every neighborhood of L, so on a real line, if there is L and every neighborhood, either closed or open neighborhood, usually neighborhood is considered to be open. So every neighborhood should contain, if the set is some S, okay? So what is the limit point of this particular blue interval? Okay, let me go back. Yeah, so let me write the interval first. So this is the set S, it's an open interval. So the limit point are these highlighted red numbers, and including all the numbers inside. How do I say that? So if I try to draw open intervals on any of the numbers which are inside S, however small I try to draw open intervals, I will include some elements of S other than that point. So that point can be these blue dots inside the open intervals. So however small I try to draw the open intervals, green open intervals around it, I will definitely have some point, at least one point of S other than that blue point, right? So but what about the border points, the border points which are not inside? Even they, however small you try to draw an open interval including that point, you are definitely gonna include at least one point of S other than the endpoints. So if these endpoints are 1 and 2, so 1 and 2 are not part of the set S, but still they are the limit points of the set S. So the question now is, how does this second definition imply the first definition? So first definition says that it should contain infinite number of members of S. So this has a stronger condition other than this here. But here the second condition says it is enough if it has at least one member of S other than the point L. Correct? So how does this second definition, I will name this number 2, imply number 1? So it is like this. Let L be the limit point. Let us assume that D2, the definition 2, is true. We have to prove this will imply definition 1. So we have to prove that. Okay, let L be the limit point of a set S. So now if I try to draw a line, the real line, because we are dealing with real line, say my limit point is here. So what would be an obvious neighborhood of L is L minus okay, let me have it a little far away. L minus delta 1, where delta 1 is a very small number to be considered, and L plus delta 1. Correct? So this open interval, let L minus delta 1 comma L plus delta 1, this is a neighborhood of L. Correct? Since L is already a limit point and definition 2 is true, there exists an element different from L, that is x1 not equal to L, such that x1 will belong to the neighborhood. Correct? Okay, then let me define a metric, that is a distance delta 2, such that x1 is here. So such that L minus x1 is delta 2, so which is less than delta 1. Correct? So in this case we have another neighborhood, that is L minus delta 2 comma L plus delta 2. That means you are bringing the open interval closer and closer. So it would be L minus delta 2, and L plus delta 2 is nothing but x1. Okay, which is another neighborhood of L. So again, L is already a limit point of S. Correct? So set S subset of R. So in that case what happens? We have and it satisfies definition 2. Therefore there exists an element, say x2 not equal to L, in S, sorry, here in S, such that it belongs to this neighborhood. So x2 will belong to L minus delta 2 comma L plus delta 2. Okay. So L minus delta 2 comma L plus delta 2. In that case, what happens? You have your x2 here. Correct? So if you continue this process again and again, you are going to bring the open intervals closer and closer. Okay, like this. And it can never end because you have infinite number. However small two real numbers you take, you have infinite number of real numbers in between. So you can take this process to the infinite number of times. Correct? So then what do you get? You get all these x1s, x2s, x3s different from the limit point that are in S. So what are you getting? You're getting back your definition 1, which says that if L has to be a limit point in R, every neighborhood of L contains an infinite number of members of S. So definition 2 definitely implies definition 1, and it is very obvious for definition 1 to imply definition 2 if you just read the statements. That is one and the same. So definition 1 interprets some results. It says that no finite set has a limit point. Correct? So if other than the limit point, if you should have an infinite number of elements inside the set, so any finite set will not have a limit point. Okay, and it doesn't mean that this statement here doesn't mean that every infinite set should have a limit point. So there is a theorem which establishes a condition of existence of limit points in infinite sets that are nothing but, that is called as Bolzano-Weierstrass theorem. Okay, so this does not imply every infinite set has a limit point. So does not imply. So what is that condition? Which tells that when can a infinite set of a real line or real space have a limit point? So that is the theorem Bolzano-Weierstrass theorem. So the statement goes like this: every infinite bounded set has a limit point. Okay, so what is a set? What is a kind of a set in R? So some textbooks define or state Bolzano-Weierstrass theorem in a different way. How do they do that? So a set in R is nothing but an example, an example for a set in R is a sequence. Correct? So generally, what do you say sequence to be? An orderly arrangement of numbers. So it's a sequence. So what do you mean by a sequence, a bounded sequence having a limit point? It means that the sequence is convergent. Correct? Sequence has a limit point means it is convergent. It's convergent. Correct? So what is the condition for a sequence to be convergent? It should have a convergent subsequence. So we will learn in detail about all this in the next chapter. But just to clear your confusion, like why some books define Bolzano-Weierstrass theorem in a different way. So I'm just giving you an explanation. So using all this interpretation that we did right now, we can change the statement of Bolzano-Weierstrass theorem as every bounded sequence every bounded infinite sequence or every convergent every bounded infinite sequence every bounded sequence okay has a convergent subsequence. Has a convergent subsequence. Okay, so some textbooks, they define things like this too using the interpretation, and you are good to go with, you can use anything. This is quite general, but this is just specific to sequences, as sequences are specific sets of real numbers. Okay, so let me define another term, that is derived set. Derived set, the set of all limit points, the set of all limit points of a set S is called the derived set. Okay, so I usually, some Indian authors, they usually represent this set by L of S. So L of S is nothing but set of all limit points of the set S. Okay, and in the textbook, whether it is Malik and Arora or some other textbook, it is defined as S prime. So you can use any of the notation denoted. You can use any of the notation, but basically I use S prime to denote S complement. So I prefer using L of S. That makes a little things easier, but yeah, so this is the denotation that I will be using. You can use S prime too. So let us now go through some of the examples of limit points. Okay. Yeah, first example is R. What about the set R itself? Okay, set of all real numbers. So let us try to analyze the definition. So R, for every point of R, every interval containing all the points of R will definitely have at least one point of R other than that point, correct? So to scarcely plot the points of R, so every interval, every open interval will definitely, however small you try to draw, it will definitely contain at least one point other than the red point plotted. That is a real number, correct? Because real numbers are dense in nature. So every neighborhood of any of a real number, any of its points, will contain infinite numbers or will contain at least one point of R other than itself. So what are the set of all limit points of R? What is the derived set? L of R is R itself. So every real number is a limit point. Second example, what about Q? So again, what are the limit points of Q? So again, when we explained an open interval above, I think I erased it. So sorry, when I explained about an open interval above, we could see those the end points were limit points, but they were not part of the set. So the same thing applies to q also here. So what happens, every point of the set q is a limit point of itself, because between two rationals there will exist infinite number of rationals again. Rationals are dense again. Okay, but again further every irrational number will also be a limit point of q. Okay, because every, if you, okay, so this is q1, q2, q3 sparsely plotted. So if these are the rational numbers, every interval will definitely consist at least one rational number other than q1, other than q2, other than q3, like that. So every rational number is definitely a limit point. But what happens to the irrational numbers? You have irrational numbers also. Apart from q1 you will definitely have infinite number of irrational numbers also. So what are the limit points of q then? L of q is nothing but the set R itself. Okay, and then next example. So every real number is a limit point of set of all rationals. So therefore the derived set is nothing but R itself for set of all rationals. So if you consider the set 1 over n belongs to natural numbers. So 1 over n, what is the limit point of 1 over n? So has only one limit point, 0, because as tends to 0 as n tends to infinity. So if you have to plot this here, 0, 1 over n, for n natural it will be 1, and yeah, it is open interval 0 and 1 kind of, right? Yes, it is open interval 0 and 1. So why 1 is not a limit point? Okay, so why 1 is not a limit point? Think on this. Let us discuss on Saturday. Because this set is nothing but 0 to 1 according to me. If it is different according to you, you should tell me. So, but why only 0 is considered to be a limit point and why not 1? Okay, so answer this question when we meet. This is a question that you need to think upon. So here in this case 0 is a limit point. Okay, so you should think of a open interval containing 1 but will not contain any other points of the form this. Okay, of this form apart from 1. Okay, so what about closed interval? Any closed interval a comma b. So again draw a line, include a and b. So it is obvious that every point inside the interval, however small open sets you try to draw, you will definitely include the points of this set inside that open interval. So what we should worry about is the endpoints, correct? So the endpoints definitely will have, again, so let me draw it in a different color. So the endpoints, however small you try to draw open intervals including the endpoints, you will definitely include the point of this set S, which is an interval, inside those open intervals. So every open interval containing A will definitely have a point of S other than A, and B, every open interval containing B will definitely have a point of S other than B. Correct? So what is the set of all limit points? It is nothing but the closed interval itself. So this example tells you that if you have a closed set or a closed interval, the set of all limit points are inside the set itself. Correct? So this is very useful in learning the properties of closed sets. So what about open intervals? We discussed already. Open intervals, limit points of all open intervals will be including the endpoints. It will be closed interval a comma b. Okay. So there are some exercises inside in the book. So obtain derived set of the following in page number 32 that I have sent in the WhatsApp group. 1, 2, 3, 4 and 5. So let us discuss this. Think upon, write down all the derived sets of the given sets, and let us think, and you need to answer it. Okay. With the I'm bouncing back to Bolzano-Weierstrass theorem again. So in the Bolzano-Weierstrass theorem, every infinite bounded set has a limit point. So boundedness is not really necessary. In order for an infinite set to have a limit point, it is not necessary condition. It is a sufficient condition. It is not a necessary condition. So how is that? So let me give you an example. So if you have a set 1 over 2, 2, 1, 1 over 3, 1 over 2, 2, 1 over 3, 3, 1 over 4, 4, things like this. So this definitely has a limit point, one limit point, which is that it is 0, because 1 over 3, 1 over 4, 1 over 5, they have the limit point 0, but it is unbounded above. It is not bounded above. Therefore, once a set is not bounded above and bounded below, it is definitely unbounded. Because 2, 3, 4 will go on up to infinity. So it is unbounded, but it has a limit point 0. Okay. So therefore, I say that boundedness is not necessary. It's a sufficient condition. You can't, once you see a sequence or a set which is not bounded, just because it is not bounded, it doesn't mean that it does not have a limit point. Okay, so then there are some properties of closure of a set. So derived set. Properties of derived sets. First one, what is it? L of S union T is equal to L of S union L of T. So you can try to prove this. Any topology book or any real book will have a proof for this. Okay, so but the same property does not hold for intersection. Okay, you can try to do it for open intervals. Say S is 1 comma 2 and T is 2 comma 3. So what is L of S? It is closed interval 1 comma 2. L of T is closed interval 2 comma 3. Correct. So L of S intersection L of T would be just singleton set 2. But L of S intersection T. First, what is S intersection T? It is null set. So derived set of null set is nothing but null set again. So singleton set is not equal to null set. Okay, these are the properties. So if you have any questions, so your question for this video would be, you need to think why one is not a limit point of this set of all 1 over n's where n are natural numbers, this thing here, and work on the derived sets, page number 32, where you have an exercise of finding out the derived sets of 5 sets. So find out what are the derived sets of them. We shall discuss it on Saturday and Sunday for you people. So this would be the end of the first video. In the next video we will learn about closed sets, and in the next consecutive video after that would be on countability. So I'm splitting the videos and making it short. Okay, see you in the next session.